All righty. A couple reminders. Hold on one sec. Oops. Tomorrow you do have a quiz over the ions, which we covered yesterday. Tomorrow's also the last day to turn in your name if you're going to do the project on the scientist. That form has to be emailed to me by 3:30. If you just verbally have asked me about somebody or just dropped me an email and said, is so-and-so available, that is not enough to reserve that scientist for you. You have to fill out the form I've shown you a couple of times. So right now I only have one person, Aaron, in this class that has done that. And once again, it's not required. So, but if you're going to do that. What we're learning today, we will have a quiz on Monday. And Friday, I will not be at school, so we will not Zoom. I'll give y'all further directions tomorrow on the things that you'll need to work on that will be due. We'll have a test over this unit next week, next Tuesday, and I'm putting together a review on quiz, so you can have that to work on over the weekend if you choose to kind of get ahead. All right, let me stop here for just a minute and do my attendance. We're going to move back to our notes over the periodic table and finish those up today. So this is our, from yesterday when we were talking about our ions. So if we look at those, francium is from group 1. So it has 1 valence electron. So it's going to lose that 1 valence electron. So it would be an Fr+1 ion. That would be true of anything that was in group 1. Sulfur is in group 16. So it has 6 valence electrons. It needs how many more?
Two more.
2 more, perfect. So it's going to gain those 2 and it would become a -2 ion. Nickel is a transition metal, so it doesn't follow any rules necessarily, but remember this right here is a little trick on this one. That tells me what the charge is, and it's a metal, so it'll always be positive, so it's a +2. And the reason it's like that is because nickel can form more than one type of ion, so there needs to be some kind of way to notate that. All righty, so moving on to our notes, we're going to talk about periodic table trends. You have practice in your Google Classroom for this, and like I said, the quiz will be next Monday. If you're a regular class, I have my one regular class second period. So if you're watching this for regular class, your practice will not be until tomorrow. So right now there's nothing in your Google Classroom. Just for my second period regular class. All right. So we know that the elements are arranged according to their atomic number. And when the scientist decided to do that, then he also decided how many groups there were going to be eventually. And by doing that, then he has elements with similar characteristics lined up in groups. So there's, when we talk about periodic trends, there's trends within a group and then there's trends within a period. And they're caused by 2 different things. So the first few slides here, there's nothing really for you to fill in. It's already all typed in for you. I'll tell you whenever you need to write something down as we kind of get started more. So the reason that we see a trend within a group is because as we move down a group, as we go from period to period down a group, another energy level is added with each period. So if this is my nucleus, that would be the elements in period 1, elements in period 2, elements in period 3, and that would continue obviously down to period 7. All of the positive that there is in this atom is in the nucleus. There's some negatives at each of these energy levels because there would be some electrons. But you can see as I add energy levels, those electrons get farther from that positive nucleus. So the attraction between the nucleus and those electrons would decrease. So that means that atom would not be able to hold on to those valence electrons as well, the more energy levels there are. One of it is just because of the distance, and the other one is because of something called shielding. And shielding is an invisible barrier made of core electrons, and core electrons are anything that aren't valence. So in this case, it would be the electrons on the second energy level and the electrons on the first energy level. Those would be considered the core. And those core electrons shield the valence electrons from the nucleus. So once again, that, just like the distance, is going to decrease the pull of the nucleus on the electrons out in the valence shell. So that's going to affect the size of the atom, and then it's also going to affect how easy it is to gain or to lose electrons. So these things that we see, shielding and also the adding of the energy levels, those are what causes a trend within a group. Trend within a group. And then if we go to within a period, we see something else. So the number of protons and electrons in the atom are going to affect the trend within a period. The more protons and electrons in the atom, the stronger the attractive forces. So as I move across a period, I'm staying in the same energy level, but my atomic number is increasing. So that means as I move across the period, I'm having more protons and more electrons. And the more protons and the more electrons that I have, the more they're going to attract each other. And this is called the effective nuclear charge, or it's also called ZF. Z, and then that's like a subscript of EFF. So effective nuclear charge, or ZF, affects the added protons to the nucleus of the elements in the same period. And because of that, they have an increased pull on the individual electrons in the orbital. And ZF increases as you go across the period. Because as I go across the period, I'm adding more protons in the same energy level. So that's allowing more attraction between the protons and electrons. The atom hasn't got any larger. There's not any more shielding. And once again, that's going to affect the size of the atom, and it's also going to affect whether an electron can be gained or lost. So effective nuclear charge, or ZEF, is what you see that causes the trends within a period. So we have one thing that causes them within a group, and then another thing that causes them within a period. I'm going to skip a couple of slides because they're kind of just repeats. Most of this slide is a repeat, but you do need to add this part right here. And it's a little bit out of order. This part needs to be added under effective nuclear charge, which is number 2. So as the number of charged particles increases, which is what's happening as I move across a period, Coulomb's attraction also increases. So that means the electrons would be held tighter by the protons. So I'm going to give y'all a couple of minutes to add that to your notes. This part right here in parentheses, you don't need to add that. It just says add to notes, as in you need to add them to your notes. All right. Now this one talks about shielding. So this part down here in red needs to be added after shielding, which is actually in part 1. So like I said, they're a little bit out of order. So he's talked about the fact that as you go down the group, you're adding energy levels. So that's increasing the distance between the protons and the valence electrons. And that increase in distance causes a decrease in Coulomb's law or Coulomb's force. So those electrons are not held as strongly. All right, so now we're going to start talking about the different trends. All right. So the first one that we're going to talk about is atomic size, radius. So that goes in that blank right under the trends. It's half the distance between the nuclei of identical atoms. So you measure from the nuclei of one to nuclei of another one. So it's a representation of how large an atom is. So you can look here, if I just look at a periodic table that has all the different sizes, you can see atomic size increases as I go down a group, which that makes sense because I'm increasing energy levels. So more energy levels, the atom's going to get larger. And then also notice it increases as I move from my nonmetals to my metals. And the reason that is because ZF is greater over here, which means I have more protons and electrons in the same energy level. So those electrons are pulled closer into the nucleus, so that's going to make for a smaller radius size. So the trend that you will see is that atomic size increases as you go down, or if you go backwards across the periodic table. So right under atomic size where it says trend and then a colon, that's where you should be showing your arrows to show what the trend is. And we're assuming that the periodic table is right here. So that's the trend within a periodic table. So like right here, y'all, where it says, or that's where you want to put your arrows at. All right, so the very smallest is helium, the very largest is francium, and it's good to know the two extremes on these trends, because if you struggle sometimes using the trends, then this may be helpful to you. So in other words, if I listed 5 atoms for you and I said, which one's the largest, you're going to want to pick the one that's closest to francium. So knowing this trend sometimes is helpful. So going down a group, we said they get larger, and once again, it's because we're adding energy levels and the shielding is increasing, and then they get smaller as I go across a period because ZEF is increasing, the number of protons is increasing, so that's pulling the electrons in more. Trend number 2 on your next page at the top, ionization energy, is a measure of the ease with which an electron can be removed. Higher the ionization energy, harder to remove electron. So the first ionization energy would be when the first electron is removed from an atom. Second ionization energy is now when an electron is trying to be removed from an ion, and that requires additional energy. Second ionization energy is going to be greater than your first ionization energy. All righty. Skip that slide. We'll go here. So helium has the highest ionization energy. That means it's hardest to remove an electron. Francium has the lowest, so that would be the element that is easiest. How am I spelling easy? E-A-S-I-E-S-T. That doesn't look right. Anyway, that's supposed to be easiest. So your trend is that it gets harder as you go up a group or as you go across the period. That would be your trend, that with arrows you would want to put there. It gets harder as you go up a group because the atom is getting smaller, less energy levels, so the electrons are held tighter. It's getting harder as you go across the period because more protons, so ZEF is higher, or the effective nuclear charge. So once again, the electrons are held tighter. Next one is ion size. We know that an ion is an atom that has lost or gained electrons. Cations are positive. And remember, cations are formed by metals, and metals have a low ionization energy and they lose electrons easily. So the metal ion, so my potassium ion would be smaller than my original atom. One, it's lost an electron, that would make it smaller, but now it has fewer electrons, one more proton than electron, so that proton is able to hold those other electrons in. Anions are negative. That's what my nonmetals do, and they have a high energy, ionization energy. And they gain electrons easily. So the ion, my oxide ion, for example, is going to be larger than my original oxygen atom. It's gained 2 electrons, that's made it larger. And then also the fact that those protons can't hold those extra electrons in as much. So the smallest is your hydrogen cation. The largest is your iodine anion. And then your trend is ion size increases across a period and down a group. All righty. Next one, electronegativity. That's a slide that needs to be taken out. We've already talked about that. So next one, electronegativity. The tendency of an atom to attract electrons to itself when it's part of a chemical bond. So this wouldn't just be an element by itself. It has to be some elements that are bound together. This is what gives water its polarity. I know y'all remember from biology that water is polar. If I have a water molecule, these lines represent a bond. And that bond's made up of 2 electrons. One contributed from the oxygen, one contributed from the hydrogen. But oxygen's much more electronegative than hydrogen, so it is able to kind of shift those shared electrons toward itself. So when you do that, you end up with a polar molecule, which is a molecule that has a slightly positive side and a slightly negative side, like you do in water. The more electronegative an element is, the more it can shift those shared electrons toward itself. So if we look here at our periodic table, this is one that you can see numbers obviously that are not atomic numbers. This is one that's just off of electronegativity. Fluorine has the highest electronegativity with the value of 4, and then everything else is relative to it. You can see that the metals have higher electronegativity numbers than the, I'm sorry, I said that wrong. The non-metals have higher electronegativity numbers than the metals because they're more likely to be able to shift those electrons. Some of the noble gases are not given a value because they would never be part of a compound. So the trend for electronegativity is it increases as you go up a group, or as you go across a period. And for those same reasons that I go up a group, I'm in trouble talking. go up a group, I'm losing energy levels. So that's like the protons in the nucleus are more exposed, so they can pull in those shared electrons more. And as I go across a period, my ZEF, or my number of protons, are increasing. So once again, that kind of allows them to make those shared electrons of the bonds shift over to them. Oops, that's not what I meant to do. All right, so fluorine is the most electronegative with the value of 4.0. Francium is the least. And our trend, once again, was increasing as you go up a group or across a period. All right, next one, electron affinity. So this is the energy change that accompanies the addition. So ionization energy was losing electron. Now we're talking about adding an electron, or the desire of an atom to have another electron. High electron affinity means electron is more easily added. So your halogens are going to have high electron affinity. Add it, yes, sir. So if we look here at our trend, electron affinity increases as you go across a period or up a group. That would be my trend. And for the same reasons, for less energy levels as I go up, or as I go across a period, my number of protons or effective nuclear charge is increasing. So fluorine has your highest electron affinity and francium has your lowest. All right, and then the last one is metallic character versus non-metallic character. We know the majority of the periodic table are metals. Well, transition true, but if we're just doing metals and non-metals, the majority of them are metals, and they have more metallic character. Metallic character, that's supposed to be a C. Increases with the ability to lose an electron. So francium would have the most metallic character of any element on the periodic table. So as I move across the periodic table from my metals to my non-metals, and that metallic character is going to decrease. Because I move over to my non-metals that don't want to lose electrons, they in fact want to gain electrons. All right, so the last on this slide right here, at the top on the last page of your notes, is kind of most of the trends put together. Remember, electron affinity and ionization energy are almost opposite of each other. Electron affinity is to add an electron And as it increases, that means it's easier. And then ionization energy means to remove an electron. And here an increase means it's harder to remove. So they're pretty much opposite of each other. All right, so down below are some examples of like what you would do using the trend. So let's just look at the first one. The first one gives me lithium, which is about right here on your periodic table, sodium, and beryllium. And then it says which one of those has the largest atomic radii. So based off of your trend for atomic radius, which one of those would have the largest atomic radii? That's right, sodium. This one right here, your Na. Because my trend is they get larger as I go down or as I go backwards across the period. All right, so why don't y'all try the other ones? I think there's 5 other ones and see if you can work through those. So I'll give you a few minutes. Well, that's not what I want to do. So let's look at these. We already did the first one we said was sodium. Oops, hold on. I think I went, let me go back one. All right, so we said that one was sodium. So which element has the lowest ionization? Selenium, that's correct.
Number 3 is nitrogen.
Actually, number 3 isn't nitrogen. It's silicon, exactly. Lowest electronegativity would be silicon. All right, now we go and we're going to look at these. Which would have the largest size, the sodium atom or the sodium ion? Remember, the ion has lost an electron. The atom has not. So which one do you think is going to be the largest?
The ion.
It's actually going to be the atom because it hasn't lost anything. Now here, when I go to my anions, sulfur is -2 because it's gained 2 electrons, or the sulfur atom like that where it has it. So which one of those do you think is going to be the largest? The ion, that's right. Which element has the highest ionization energy? Anybody have a guess for that one? That one would be oxygen. And then which element has the highest electronegativity? That's going to be, that one should be easy because we said already that fluorine is the very highest of all. So like I said, there's a couple of different ways to approach this with the trends or with looking at your extremes. If you go into your Google Classroom, y'all have y'all's on paper, but this is for my honors. If you go into your Google Classroom, then under practice, you have periodic table trends practice. And just like we've done before, it's practice. So you can practice it here and then you can go and check yourself because you have your answers included. And practicing on this is something that makes it better or something you will get better at. All righty. So we will end right there. I had somebody that send me in the chat room, what are we doing? We were doing the lesson and it's now complete. So if you missed it because you were late, then you'll need to go and watch it on the YouTube channel because will be recorded and it will be there this afternoon about 4:30. All right, I'm going to let y'all go on. You really need to do your practice on this. It's hard to be successful if you don't practice on this. And then tomorrow we'll continue on our Chromebooks. All righty. I'll see y'all tomorrow.